Hello, this is Mr. Collier, and today we're doing some probability formula and Venn diagrams. Okay, so first let's look at some basic probabilities like if I toss a coin, theoretical probability of a head is obviously half. This is one of the most basic probabilities, a coin toss. We're going to look at a lot of coins and some dice rolls in a second. So if you toss a coin 100 times, then you would expect to get heads half of the time, so that would be half times 100, which equals 50. So we're going to use that concept in a bit. Sample spaces. So sometimes the best way to work out all the outcomes is just to list all the possibilities. Otherwise, sometimes you can shortcut it. If I toss a coin twice, the possible outcomes are heads, or the first one's heads, the second one's tails, heads, or tails. Okay, so there's 4 different possibilities, and this is called the sample space. Maybe we can use set brackets. This is the set of all the 4 possibilities, right? So if you want to work out probabilities like the theoretical probability of one head, one tail, then that probability is, well, there's 2 of those possibilities, so it's 2 out of 4, which is half. Next, if you toss a coin 3 times, the possible outcomes, so you can list them all out. Heads, 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 tails, heads, tails, heads, tails, heads, heads. So that's all the possibilities there with one tail, or you could have heads, tails, tails. Kind of want to be systematic with this. And then tails, tails, heads, and lastly you can have tails, tails, tails. That is 8 possibilities. Okay. So notice this was 4, and this one was 8. You always get powers of 2 because there's 2 possibilities, heads or tails. So you're always going to get powers of 2 with the coin flips. Anyway, next is 2 dice rolls. So it's important to know this kind of thing for dice rolls. And these are the sums of dice rolls here, okay? So if you roll 2 dice, you got 1 to 6. There's actually 36 possible outcomes when you roll 2 dice. Very important when you're working out dice probability, even for board games and stuff. So what's the probability of getting a total or a sum of 7? The probability of sum of 7 is, well, you can just count the number of possibilities, and there is 6 of them out of 36. It's the most likely outcome when you roll 2 dice. That's why you call it lucky number 7. Okay, so that's 1/6, or approximately 16.7% if you like percentages. So it's important to know this little grid when you're doing dice probabilities. Given that the score on the first dice is 4, give the conditional probability that the total is 8. So the way you write that is find the probability of getting a total of 8 given the first is 4. I guess you could say it like that. So this vertical line means given that. So that's how you write it, a big vertical line. So this is not the same as the probability of 8. The probability of 8 is 5 out of 36, but we're just looking at the possibilities where the first number is a 4. So this basically changes the denominator because you're not looking at all 36 cases now. You're just looking at the cases where the first number is a 4. And there's 6 cases where the first number is a 4, and only one of them has a sum of 8. So actually the probability is 1 out of 6. You can also use a formula in your IB formula booklet. So the probability of an event A happening given that B has occurred is probability of A and B divided by probability of B. Okay? So this denominator, look at the probability of B. That's basically probability that 4 has occurred. So that's why there's a 6 there, basically. Anyway, and well, let's work it out with the formula. So the formula, you got a probability in the numerator and denominator, not just the number of outcomes. So here this would be 6 out of 36 ways that the first number is a 4. Okay, given that a 4. So the probability of the first number being a 4 is 6 out of 36. And the numerator should be the probability of sum 8 and first is 4. Okay, your denominator was probability first is 4. So what's the probability the sum is 8 and the first number is a 4? There's only 1 in 36 ways that can happen. There's only one. This is the only way. The 36's cancel, and you just get 1 out of 6, so it matches the same thing. Now the formula is useful in some more difficult cases. Sometimes it's easier just to do it like we did it here in red. But sometimes the formula is the only way to go about it. Okay, given that the score on the first dice is odd, so we're given first is odd, find the probability that the total is 8. Alright, so we can narrow it down. We can use the formula. Maybe we won't use the formula for this one. So we're given that the first one's odd. So let me put that in blue. First one's odd is, oops, that's quite large there. We're given the first one's odd. So that's 1, 3, 5. Those are odd. Well, basically half of them are odd. Okay, so your denominator is now 18. All right, and your numerator, find the probability that the sum is 8. So we just need to look at these blue rows here. And we have one possibility is an 8 and another possibility is an 8. So we have 2 out of 18, which is 1/9. Okay, and you can work it out with conditional probability as well. If you would use the conditional probability formula, your numerator or your denominator is the probability the first one's odd, and that's half. Okay, and the probability of a sum of 8 and the first one is odd is 2 out of 36, like we just did right there. That equals 2 out of 36 times 2 out of 1. Divide, you multiply by the reciprocal. And that simplifies to 4 out of 36, or just 1/9, so it's the same thing. So you can also use the formula, but sometimes it's not the easiest way. Let's make some Venn diagrams now, which are useful for some probability questions. Consider the set U consisting of integers from 1 to 10. So let me write that out. This is set notation. 1, 2, all the way up to 10. So that's 10 numbers. And then A and B are these sets. Show this information in a Venn diagram. So Venn diagram consists of 2 or 3, possibly more. I guess I can write U on the outside here. So let's look at the middle, which we call the intersection first. Which numbers are in common? 3, 6, 9. Only 6 is in common. And numbers that are in A, also the other numbers that are in A are 3 and 9. And for B, we have 2, 4, 8. And outside the Venn diagram, we need all the other numbers from 1 to 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and up to 10. So 10 goes there. So all 10 numbers are here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes. So the diagram is complete. This notation means the number of items or number of elements in a set. Number of elements in set. So set A obviously is 3. Not in set A is, well, you can count, but it's just 10 minus 3, right? Actually, let me write that out. Like, it's just 10 minus the number in A, which is 7. Find the probability of selecting an element from A where a single element is chosen from U is this, of course. Yeah. So A there's 3 elements in A, there's 10 in U, so it's 3/10, obviously. There's a 3/10 chance of selecting one of these numbers. This is called the intersection. Okay, let's talk about this middle part here, really. Intersection. Also, we often just call this AND. What's the probability of A and B? What's the probability of a random element being in A and B? And you can see there's only one of them there, so the probability is 1 out of 10. Okay, that's the intersection. This is the union, or you could call it OR. What's the probability of an element being in A or B? So then the Venn diagrams, let me draw the Venn diagrams for this. If you're looking at all the elements in both A and B, that's A union B. And if you're looking at this is the intersection A and B. Okay, so the union is all the elements in all of these, including the overlap. 1, 2, 3, 4, 5, 6. So that's 6/10. Okay. Now for these next ones, the easiest thing to do is look at the Venn diagram. So these are elements not in A and in B. Don't forget this. This is the intersection. It can mean and. You can think of it as and. Not in A and B. Well, these are the elements in B, and the ones that are also not in A are these three elements right here. So it is 3/10. Not A union B. So that's everything in both of these sets all together included. So maybe I could even do a little mini Venn diagram. Okay, so they're not in A. So not in A is all the stuff outside of A. Okay, union with B means you got to include everything in B, so even the intersection. So it's basically everything except for the 3 and the 9 here is that union. So that's 8 out of 10. This is elements not in A, and they're not in B. That would be all the elements here are the elements that are not in A and they're not in B. So that's 4 elements, 1, 5, 7, 10, right? So 4 out of 10. And union, not in A, union not in B. So let's do that. So you can highlight everything that's not in A. And then this is B. Everything that's not in B includes this part right here. So it's everything except for the intersection. Okay? So that is actually 9 out of 10. So you can do a lot of this probability stuff by just looking at Venn diagrams. Okay, let's move on to a word problem. So a class of 30 was asking which of the 3 major holidays they went abroad. Okay, so 3 major holidays means we're going to do a 3-circle Venn diagram. Okay, and we got summer, Christmas, and Easter. Summer, Christmas, Easter is class of 30, blah, blah, blah. 2 went away on all 3. That's a nice piece of information because you could stick that right in here. 6 went away in both summer and Christmas. 6 went away in both summer and Christmas. You gotta be careful. That's this whole piece right here. Summer and Christmas, this whole sliver here should be 6, but that means this has to be 4, not 6. Okay, so we got that piece. 5 in Easter and summer. Easter and summer is this whole thing here. And 14, let's see now. 6 in Christmas and Easter. Christmas, Easter should be 6, so that's a 4. If 14 go away in summer holidays, that means this entire circle should be 14. Right now we have 9 in here. So this should be a 5. So you can work it out slowly and logically. You get it all correct in the end. 16 is the Christmas holidays. This is already 10, so that's a 6. 11 in Easter holidays. This is already 9. This is already 9, so this should be a 2. Okay. Now there could be some that do neither, and well, that's what it's asking right here. Basically, you use the factors 30. So you do 30, subtract 5, subtract everything in these diagrams. I don't know, maybe you can just do it manually here. If you do 30, subtract all these numbers that I've written out here. You get 4. Okay, so that's 4. Now let's answer these questions. Find the probability he goes abroad during summer or Christmas. Okay, probability of summer or Christmas. So that means you can look at the entire circle for summer and Christmas, okay, and add those all together. So that equals, I should have written it down there. Wow, this is 5, 10, 24. There's 24 in there divided by 30. Okay, and you can simplify that, or actually, let's simplify that because it works out to a nice percentage. 8 over 10, or 80%. That's a nice statistic to work out there. Number 2, he or she goes on abroad at Easter given that they go abroad in summer. So the given probability, that's a conditional probability. We're working out probability of Easter given they go away for summer. So if you want to do it from the Venn diagram, that means you just look at the summer people. This circle right here, we're only looking at people who went away in summer. What's the probability they also went away in Easter? That's 5 out of the total summer people, which is 14. You could also use the conditional probability formula, but for Venn diagrams, it's probably easier to do that. Okay? But if you use the conditional probability formula, you can do probability of E and S divided by probability of S. E and S, that is 5 out of 30. Probability of summer is 14 out of 30. So you see what happens here. The denominators cancel, and you do get 5 out of 13, the same thing. But you can use the Venn diagram if you want to for those simple problems. Okay, next we're going to explain some of the rules in the formula booklet using a Venn diagram. So yeah, it's easy to explain the rules in your formula booklet and even create new rules with a simple Venn diagram like this. So one way to think of the union, now the union is all of this and this together, is you can take all of A and add it together with all of B. But then you see you're counting the intersection twice. So that's why in the formula booklet you have the union equals A plus B and then minus the intersection. Okay, so that's how you can explain the rule using this Venn diagram. So the union equals probability of A plus probability of B minus the intersection because of this, right? Notice you could move this to this side and move this over to the other side, so you can rearrange it so that this is the intersection, this is the union, and you can use that formula as well. But in the formula booklet, we have it listed as this. Okay, it says combined events here, but it pretty much works for all events A and B, basically. So this is a very important rule that works for all events A and B. Now, let's do some questions down here. Probability of A and B. Well, that if we have A and B, so what we can do is like what I just said. You can swap this and this here. So the probability of A and B equals probability of A plus probability of B minus. You can swap those around, and you can say the union, right? Oh, sorry, A union B. So then you just take these numbers, 0.4 plus 0.5 minus 0.6 is 0.3. Okay, the next example, this is not A. So not A, you can do 1 minus probability of A. Those are complementary events because they have to add up to 100%, right? A and not A for any events adds up to 100%. So you can do 100% minus the probability of A. It gives you the probability of not A. And that is, of course, 1 minus 0.4, which is 0.6. And probability of A union not B. So sometimes you don't refer to a formula in the formula booklet. You can just kind of draw a diagram to figure out what that represents. And then just, actually, let's go back to this diagram and fill in the numbers that we just calculated. So probability of, now we have the intersection is 0.3, and we know probability of A is 0.4, so this has to be 0.1. Probability of B is 0.5, so this has to be 0.2, so that the whole circle is 0.5. These numbers add up to 0.6, so this has to be 0.4 because they all add up to 1. And now let's go back to this diagram. A union B, well, you would highlight all of A, union that with not B. So not B is everything outside of this circle, so you would include this as well. And then you can add up these probabilities here. 0.1, 0.3, 0.4, that gives you 0.8. Okay, next one here. not A union B. So let's draw the Venn diagram. Not A is everything outside of A, include this. Union B, well, you highlight all of B, so including that. So you want all of those things. Or you can do 1 minus this section, so it's obviously 0.9 because that's a 0.1. Okay. So sometimes, drawing the Venn diagram can help you out a lot rather than trying to manipulate formulas. Okay, mutually exclusive events. Now, you don't really even need this formula in the formula booklet. It's the same as the one on the top. If they're mutually exclusive, then A and B have nothing in common, so this term just becomes 0. So obviously, the formula becomes this, right? The Venn diagram just looks like two non-overlapping circles. So these are what mutually exclusive events look like. So obviously, the union is just adding them together. So probability of A union B is just probability of A plus probability of B. Okay, conditional probability, you can explain this on a Venn diagram as well. And let's go into this now. So in the class of 22, we have football and hockey. All right. So I'm going to show this in the Venn diagram. Football with an F, hockey. 22 students, 13 play football, 14 play hockey. Now 13 plus 14 is 27. Okay, so we have 27 total in these two circles. 5 play neither, so we put a 5 out here. Put that in a different color. 5 play neither. So the two circles together plus, well, let's do that. 27 plus 5 is 32, but there's only 22 students. This means there must be 10 in the intersection. Okay, and the hockey players are 14, so there must be a 4 here. Football players, there's 13 of them, so there must be a 3 here to make this 13. All the numbers make sense, you can double check it, and there's our Venn diagram. Find the probability that the student chosen at random plays football and hockey. That's probability of football and hockey. That is just the intersection divided by the total, which is 22. Okay, now part C. Plays football given they play hockey, so probability football given hockey. Now you can use the formula in the formula booklet, but I'm going to do it logically first and then show how it's equal to the formula in the formula booklet. So if it's given that they play hockey, you're only looking at the hockey players. So there's 14 of them, that's why the denominator is 14. And out of those 14, 10 also play football. Okay, now with the formula, you would do probability of F and H divided by probability of H, according to the formula. Let's look at that formula again. So the given thing goes in the denominator, right? So the given thing is probability of H. Probability of H overall, there's 14 hockey players. There's 14 hockey players and 22 total. And the numerator here is probability of football and hockey. That is 10 out of 22. And you see the 22s cancel. You can multiply the numerator and denominator by 22 and you get 10 out of 14, which is the same. So Venn diagrams are easy to do without the conditional probability formula. But later when we do tree diagrams, the formula is very essential. Okay, plays hockey, given not football. Okay, let's use the formula this time. Hockey and not football divided by probability of not football. Okay, hockey and not football. How many people play hockey but not football? That's 4 of them. 4 play hockey and not football, so that's 4 out of 22. And the probability of not football, we have 13 football players. So not football would be 9 of them. So 9 out of 22, which simplifies to 4/9. Okay. So this is basically deriving the formula in the formula booklet. You know, if you got A and B, and you're doing probability of A given B, you just look at the B section for your denominator. Okay, and the intersection for your numerator, and the intersection is A and B. So that's kind of where the formula comes from. Okay, next, shall we do the next one? Okay. Yeah, let's do this. Some of these things we can use the formula, or you might want to draw a picture sometimes. Let's see. The union, we can use the formula, the first formula from the book. This is probably the most useful. The union is A plus B minus the intersection, which is 0.5 plus 0.6 minus 0.4, that's 0.7. And this, we can use the formula, probability of A and B divided by probability of B. Probability of B is 0.5, the intersection is 0.4, that was pretty easy, it's 4/5. Here, very similar, your numerator is going to be B and A, but your denominator is A this time. So that is 0.4, and A is 0.6, so it's 4/6, or 2/3. And the last one here, yeah, let's see now if we can do this. You want not B and A divided by probability of A. The denominator is easy enough. A is 0.6. There's formulas for that out there, but it's probably best to just draw a diagram and put in the information we have already. We have the intersection 0.4. Probability of A is 0.6, so that's 0.2. Probability of B is 0.5, so that's 0.1. That means there's 0.3 out here. This all adds up to 1, so this looks correct now. So not A and B are elements that are not in B and they're in A, so that's the 0.2. Okay, so that's 2/6 or 1/3, if you will. Okay, so notice we used the formula, but then the Venn diagram helped us out for the last one. It's often really useful to be able to draw that Venn diagram. Okay? Alright, let's take a look at the next one, perhaps. Or maybe we'll skip to another one here. No, we need to do this one. This is a little bit different. This one down here. So if two events are independent, this is the last formula in our formula booklet. It's the definition of independent events. Then the probability of A and B equals probability of A times probability of B. Okay, this is kind of like a definition rather than a formula like the other three. Okay, so if you want to prove they're independent, you can multiply and see if it equals the intersection. Or if you want to prove it's not the case, then you show that they're not equal. Okay, and this formula can come straight from this here. Okay, so if we want to rearrange this, we can have probability of A given B times probability of B equals probability of A and B, right? But if they're independent, the definition of an independent is that A does not depend on B. So it doesn't matter what the probability of B is, A doesn't depend on it. So this becomes just probability of A times probability of B equals probability of A and B. So that's where the formula comes from in the formula booklet. Okay? And that's useful because this means if you want to find the probability of A and B, you can just multiply the events together. Okay? If they're independent events, you can do that. Okay, let's look at some examples here then. If A and B are independent events, and they give you these probabilities, find this. So this is conditional probability, so we use the conditional probability formula. Okay, but since we know they're independent, we know that this is just a multiplication. It's just probability of A times probability of B divided by probability of B. Actually, the B's cancel, so it's just probability of A. Actually, we kind of did that in the previous page. That kind of makes sense, right? A does not depend on B, so it should be just probability of A, so it's 0.2. Could have probably just skipped that. Now they are independent, so probability of A times probability of B equals probability of A times probability of B. You can only do that if you know they're independent. And this is 0.2 times 0.4 is 0.08. Okay. The union, well, we can use that first formula in our booklet again. Probability of A plus probability of B minus probability of the intersection. So we have those numbers, 0.2, 0.4, and the intersection is 0.08. Okay. So that's 0.6 minus 0.08, which is 0.72. Oh, not 0.72, 0.52, I mean. Okay, next we'll do a couple more examples. Sometimes, yeah. All right, let's check it out. Yes, this is kind of like we did before. Sometimes a Venn diagram helps us out a lot. Okay. Now, probability of A and B, we are not given that they are independent, so we cannot use that last formula. We have to use the first one again. Okay, and remember you can rearrange these two. So the probability of A and B equals A plus B minus the union. Okay, so that's 1/4 plus 1/3 minus the union. Looks like we have a common denominator of 12, 3/12 plus 4/12 minus 6/12 is actually 1/12. 1 out of 12. Alright, part B is conditional probability, so you can use the formula. It's all about those formulas in the formula booklet. We have the intersection from part A. Probability of B is 1/3, so it's like one way to do it is to multiply the numerator and denominator by 12, and you get 1/4. Okay, next, again, conditional probability. Probability of not A and B divided by probability of the given thing, which is B in this case. Here it might be handy to use a Venn diagram. A, B, let's put in some numbers that we calculated already. The intersection is 1/4. A is, wait, no, the intersection is not 1/4, is it? No, the intersection is over here, sorry, it's 1/12. Okay, 1/12. A is 1/4, so this means this is 2/12, right? 1/4 minus 1/12 is 3/12 minus 1/12 is 2/12. And for B over here, this is 1/3, which is 4/12, minus 1/12 is 3/12. That's all together 6 out of 12, so 6 out of 12 is over here, so that they all add to 1. Now once you got the Venn diagram filled out, you can do any old probability you want. So not A and B are things that are not in A and they're in B. That's this thing. So it's 3 out of 12, and the probability of B is 1/3. We can multiply the numerator and denominator by 12 to get 3 out of 4. It's just 3/4, okay? And part D is just very similar, just kind of the other way around.